Okay, so we're going to move on to Unit 5, the periodic table. So we just talked about electrons and their locations along with electron configuration and how light is released or emitted from an atom. So Dmitri was a Russian scientist, and he was given credit for the periodic table. Now, he arranged his periodic table by increasing atomic mass. Now, he left spaces because he knew an element belonged there, but it was missing based on properties of the other elements. So he left blank spaces on purpose for these undiscovered elements. Now today, our periodic table is arranged by increase in atomic number. If you look at the masses, the atomic masses of each element, they look like they go in consecutive order, but some of them do not. Some of them vary. But atomic number is what our table is arranged by today. Now this slide is a review again. So remember, columns which go up and down are called groups or families. And there's 18 of them. But when we talk about valence electrons, remember that we skip the transition metals. So it's only groups 1 through 8. So groups have similar chemical properties because each element in the group has the same number of valence electrons. And remember that valence electrons are those electrons found in the outermost energy level. Now, remember, to calculate the number of valence electrons, we look at the group number. So if you look at sodium, who's in group 1, which means sodium only has 1 valence electron, versus chlorine, who's in group 7, has 7 valence electrons. So again, valence electrons just correspond to the group number. Now rows, which are horizontal, go left to right, are called periods. Remember, there are 7 of them. And the period corresponds to the number of energy levels found in that element. Now remember that levels could also be called shells. So they could be called energy shells. Each element in the same row or period has the same number of energy levels. It doesn't vary within a period. The only thing that varies within a period are your valence electrons because you're changing groups, not periods. Now, many of the properties of atoms depend on not only their electron configurations at the last unit, but now how strongly their valence electrons are attracted to the nucleus. So how are those outer electrons affected by the nucleus? This is a review as well. Go ahead and fill in a periodic table like this with your family. So group 1, alkali metals except for hydrogen. Group 2, alkaline earth metals. The middle groups are transition metals. Then group 16, where oxygen is, are the chalcogens, and then halogens, and then noble gases. Metals. 2/3 of the periodic table are metals. Remember that there is a black line on the periodic table, which we call the staircase. So the metals are located to the left of the staircase. Properties include they're lustrous, which means how shiny something is. Ductile, how they can be drawn into wire like copper is. Malleable, they can be hammered into shapes like gold into jewelry. And they're also good conductors of heat and electricity, which means heat and electricity can flow easily through them. And they are hard. The nonmetals on the right side of the staircase, and there's not very many of those. Don't forget about hydrogen, though. They are good insulators, which means they are poor conductors of heat and electricity. They are gases, but if they are a solid, then they are brittle. You only have one liquid nonmetal, which is bromine, and you have one liquid metal, which would be mercury. They are not shiny. Your metalloids are found on the staircase, above and below. So they are between the metals and the nonmetals. The only element that is not a metalloid that touches the staircase is aluminum. Okay? So their properties are intermediate, meaning they have both nonmetal and metal properties. And the main property you need to know are semiconductors. So silicon and germanium are used to make computer chips. So we combine those two, which are metalloids, in order to create our computer chips. Go ahead and label another periodic table. So color in your metals and color in your metalloids and then your nonmetals. Again, do not forget hydrogen is a nonmetal and aluminum is a metal and not a metalloid. You only have 7 metalloids. So when we talk about periodic trends, we want to focus our attention to francium, which is in the bottom left, and fluorine top right. So we're always talking about going towards francium and going towards fluorine. Atomic radius is one of the most important properties of an atom or ion, and that is its size. So atomic radius is the distance between the nucleus and the valence shell. Atomic radius increases going down a group, and why does it do that? That's because you're adding energy levels. Remember again, period number corresponds to energy levels. As you go down a group, your period number increases 1 to 7. So we're adding more energy levels, so our atom gets bigger. For example, lithium is in the second period, so it has 2 energy levels, versus francium, which is in the 7th energy level, so it has 7 rings, versus lithium, which only has 2, so francium is bigger. Now, atomic radius is going to decrease going to the right, and that's because there's an increase in nuclear charge. When we talk about nuclear charge, we're talking about the number of protons in the nucleus. Okay, remember, we're in a period, which means our energy levels are the same. The only thing that's changing is the number of protons in the nucleus, and of course, the number of electrons in the energy levels. Now, the more protons we add and the more electrons we add, there's a more of attractive force between the protons, which are in the nucleus, and the electrons. So the nucleus is actually going to pull those rings energy levels closer to itself because, again, those protons are attracted to those electrons. Opposite charges attract. So here's a visual representation of atomic radius. As you can see, transition metals are skipped again, so we're only looking at representative atoms. So as you can see, going down group 1, lithium to cesium, cesium is bigger because it's further down. And then going from lithium to fluorine, again, fluorine is the smallest because you have an increase in nuclear charge, so there's a more of attractive force between those valence electrons and the nucleus. Go ahead and get out another periodic table. I colored francium red and fluorine green. When we talk about periodic trends, we're always talking about going towards fluorine and going towards francium. So it's always down a group and to the right. So again, atomic radius, as we go down a group, it increases. So my arrow is pointing down, and I have put increase. And then I have an arrow pointing towards fluorine, and atomic radius decreases going towards fluorine. So I have an arrow, again, pointing to fluorine with it decreasing. Now, ionic radius. Remember that an ion is just a charged atom. So if we either lost electrons or we gained electrons. Cations are metals that have lost electrons, so they're positively charged, and cations are smaller than their parent atom, and that's because they lose their valence shell. Because they lose their valence electrons. Remember, metals are going to lose their valence electrons. If there's no electrons in the outer energy level, it's gone. So cations have got to be smaller because they've lost something. Remember that anions are just nonmetals that have gained electrons to become negatively charged. Anions are larger than their parent atom. Okay, we're not changing energy levels, we're just adding more electrons. So as we add more electrons to the valence shell, the electrons are negatively charged, and if you put 2 electrons near each other, they're going to repel. So we're basically packing the valence shell with electrons, which are going to make them repel. So they want to get away from each other as far apart as possible, so their radius becomes larger. Another term we can talk about is isoelectronic. And isoelectronic is, iso again is same, electronic is talking about the electrons, so same number of electrons. And if we look at nitrogen, N-3, O-2, F-, Na+, Mg+2, Al+3, all of them have 10 electrons. So all of those are isoelectronic to neon because neon has 10 electrons. Remember that atoms are going to lose or gain electrons in order to become a noble gas because the noble gases are the most stable. Here we have a visual representation. The first one is sodium. You can see that sodium atoms are to the right. They become smaller once they become a cation. Your nonmetals or your anions are to the right of the picture. As you can see, when we become an anion, our radius becomes larger. When we talk about ionization energy and electronegativity, we need to talk about the shielding effect. And the shielding effect is just where your core electrons block the attractive force between the nucleus and the valence electrons. So the more core electrons you have, those not located in the valence shell, are going to take up all of the attraction for the nucleus. So those valence electrons are not going to get very much of the pull of the nucleus. So ionization energy is just the minimum amount of energy needed for an atom to remove an electron from the ground state. When we talk about first ionization energy, that's the energy required to lose the first electron. So you can also have second ionization energy, or you can have third ionization energy. And realize that as you remove one electron, the nucleus will have a greater pull. So ionization energy increases the more electrons that you remove. So the greater the ionization energy, the more difficult it is to remove an electron. First ionization energy is going to decrease going down a group, and that's because of the shielding effect. If you look at francium, it has 87 electrons. It has 86 core electron and 1 valence electron. So those 86 core electrons are going to block the nucleus from getting to that 1 valence electron. It doesn't care about that 1 electron, so it's going to give it up easily. And then first ionization energy is going to increase going to the right, and that's because of SARS, small atomic radius. So fluorine has the highest first ionization. Well, when we talk about fluorine and francium, fluorine has the highest ionization energy because those electrons are so close to the nucleus does not want to give them up. So it's going to, of course, not give up those valence electrons. Your noble gases really have the highest because they have the full energy level, so they're most stable. But again, when we look at trends, we're only talking about francium, and we look at fluorine. So go ahead and get out of the periodic table and color it in. Again, francium red, fluorine green. I have an arrow pointing down the francium, which decreases going down, and then increases to the right going towards fluorine. Electronegativity is the opposite of ionization energy. So electronegativity is a tendency for a bonded atom to attract an electron to itself. So this means that the atom has a greater attraction for an electron, so it's going to pull the electron. Electronegativity decreases going down again because of the shielding effect. Remember, metals don't care. They don't want to gain electrons. They want to give them up. So they have a lower electronegativity than your nonmetals. And then electronegativity is going to increase going right, again because of SARS, the small atomic radius. Those electrons are so close to the nucleus, they just need 1, 2, or 3 more electrons to become stable, so they're not going to give up anything. Okay, they're going to take everything. Fluorine has the highest electronegativity value, which we give it 4. So remember that fluorine has the highest and it's 4, and again, francium is the lowest. Go ahead and color another periodic table. Here again, francium red, green is fluorine, decreasing towards francium, increasing towards fluorine. Reactivity of metals increases going down. Remember that metals want to lose electrons, so those electrons that have a low ionization energy are the most reactive. So francium is the most reactive metal. It's going to decrease going right because you have a decrease in metallic characteristics. You're going from a metal to a metalloid to a nonmetal. So reactivity, of course, is going to go down because you have your nonmetals on the right. And that's also because your ionization energy is going to increase going to the right. And again, francium is your most reactive metal. So again, go ahead and fill out a periodic table. Francium red, fluorine green. I'm increasing towards francium and decreasing towards fluorine. Reactivity of the nonmetals, it decreases going down. So remember, nonmetals want to gain electrons, so they're going to have a high electronegativity. So electronegativity decreases going down a group, and so does the reactivity of nonmetals. It increases going to the right because electronegativity increases going to the right. So remember, fluorine has the highest electronegativity value, which means that fluorine is the most reactive nonmetal. Again, draw your periodic table. Francium red, fluorine green. We decrease going to francium because it's a metal, not a nonmetal. And we increase going to fluorine, again, because of electronegativity. Nonmetals want to gain electrons. So fluorine is your most electronegative element. Again, when we look at the periodic trends, we're always looking at francium and fluorine. Francium has the largest atomic radius, which means it has the lowest first ionization energy and the lowest electronegativity. Where fluorine is the opposite of that. It has the smallest atomic radius, which means it has the highest first ionization energy and the highest electronegativity. Your diatomic elements are elements that are naturally occurring. and they contain 2 molecules of the same element. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. If you look at the periodic table, they make a 7. So hydrogen and then nitrogen, oxygen, fluorine, they make a 7 with hydrogen. Or some people call it the hockey puck and the hockey stick. Okay, so I'll go ahead and draw a periodic table. I colored mine blue. So HNOFClBrI. When they are by themselves, are always in 2. So H2N2O2F2Cl2Br2I2. Always in nature. So when you talk about breathing in oxygen, oxygen is by itself, so it's actually O2 that you're breathing in because oxygen is a diatomic element. Isotopes versus allotropes. So isotopes, remember, are the same element but has a different mass. So same number of protons, different number of neutrons. And allotropes are the same element, but they have a different internal structure. So when we look at carbon, remember, graphite, that's found in your pencils, is carbon, and diamonds is carbon. Both carbon, but they have a different structure, so they have different properties. So there's diamond on the left and graphite on the right. Different structure, same element. And that's the it for periodic trends.